All right, time to make math a little bit easier. Let's look at mole mass and mole volume conversions. This is going to make it look easy. Be able to define standard temperature and pressure. We're actually going to do that at the end of this lecture. And molar volumes. That's going to be at the end of the lecture. Convert between mass and moles and convert between volume and moles. And if you've taken physical chemistry, you recognize that putting good conversion factors together just allows you to solve more equations later on. So this is really a set up lecture, and you might want to come back to this later on when we cover things like stoichiometry or gas laws if we get to that. So mole mass relationships. 1 mole of an element is the molar mass of that element. So you remember that carbon has that 12.011 underneath it on the periodic table square. Well, 12.011 grams is the molar mass of carbon. 1.0079 is the molar mass of hydrogen. These are just things that you learn when you look at these long enough. So 1 mole of a compound, though, is the molar masses of all elements in that compound added together. So you're going to multiply by these subscripts. So C6 means if you want to do C6H12O6, which is glucose, then you want to do C6, which is 6 times 12.011. H12, that'd be 12 times 1.0079, and then O6, which is 15.99 times 6, because 15.99 is the molar mass of oxygen. So put all those together and you're going to get the mass of 1 mole of C6H12O6. And for a formula unit like NaCl, your basic sodium chloride, then that's going to be the molar mass of sodium plus the molar mass of chlorine. And that tells you the mass of a mole of that substance. So if you wanted to convert back and forth, you're going to convert using the masses of that substance. So what's molar mass of oxygen? Well, this is one of these problems. If you're just thinking oxygen like monoatomic, which doesn't exist in nature, then 16.02. Oops, not 15.99, as I said earlier, my bad. If O2, though, then it's 32.04 because it's a formula mass, because that's a molecule you're talking about now. So you actually need a formula. So if someone says, like, hey, what's the molar mass of oxygen? Well, the gas or the single atom really makes a big difference for this. And that's going to be true for all of the diatomic elements. Here's your conversion factor, the molar mass divided by 1 mole, or 1 mole divided by the molar mass. If you're setting up your picket fence, or if you're multiplying things and canceling them out, here is what you'd want to set up for this. And again, use your periodic table. Oh, so handy. What about volume, though? Well, if we think about volume, we can think about Avogadro's hypothesis, and that's going to be that equal volumes of gases are going to contain equal numbers of particles if they're at the same temperature and if they're at the same pressure. And the rationale is, for a very light gas, you have very small particles and they're not very dense, so it doesn't weigh a lot. Think of a hydrogen balloon. But if you have a very dense gas, like let's say a balloon of chlorine, which is the absolute worst thing to give at a birthday party, that's actually going to be larger particles, and they'll make a denser gas, which is actually going to end up in a smaller volume. So small particles make a larger volume compared to their size, and large particles make a denser volume compared to their size. So what you end up getting is the specific temperature and pressure. The gases of different substances will occupy the same volume if there's the same amount of molecules. So that's going to be, well, here's your standard temperature and pressure. Temperature, 0 degrees Celsius. Why? Because that's easy to measure. That's pretty standard for, just set it at 0. Pressure, set it at 1. That's 1 atmosphere, or 101.3 kilopascals. So if you set things to 0 and 1, then at this temperature and pressure, 1 mole of any gas is going to occupy 22.4 liters, and it's going to weigh the molar mass of that gas. Well, plus the balloon, if you have the balloon there. So what happens at different temperatures and pressures? Well, that's going to be chapter 14, where we look at different gas laws. It's not going to be something we're going to be doing just yet. But you can make these conversions on your spare time if you feel so inclined.